I'm going to get started now. So I'm James Hogan. I work for Imagination Technologies, pretty much mostly on MIPS kernel stuff. So just out of interest, how many of you have, would you consider yourselves having a passing familiarity with MIPS? Anyone? Okay, cool. So I'm going to look at a few things. The two main approaches to virtualizing MIPS, so it's trap and emulate and MIPS VZ, the latter being hardware virtualization, assisted virtualization. I'm just going to touch on a few particular technical considerations, which has to be taken into account. And then I'm going to look at the future work, stuff that still needs to be done. So trap and emulate's the first approach that you can use to emulate a MIPS processor on a MIPS with KVM. The basic approach is to run the whole guest operating system within user mode. And this actually allows it to run on all sorts of existing hardware that's out there, even without various newer features which are available in newer cores. So some of the things I'm going to be looking at, the problems are easier to solve with these newer features, but in order to get compatibility with as much hardware as possible, we don't use them. So the MIPS instruction set's actually quite well suited to this approach. Essentially, all sensitive instructions in MIPS aren't exposed to userland, so we don't need to trap any normal userland instructions, only instructions that would normally execute in kernel mode. And so by running these the entire guest in user mode, you always get a trap whenever an instruction that needs to be handled occurs in the guest. This is mostly coprocessor 0 instructions. These allow management of privileged states such as memory management for like the MMU, and interrupts, exceptions, that sort of thing. However, it does require a modified guest kernel. We'll get into that in a minute, why that is. This was implemented by Kemel systems for MIPS technologies. This was basically a stepping stone towards full hardware-assisted virtualization. It's now upstream in Linux 3.10, and I've since upstreamed the QEMU patches in QEMU v 2.1. So this is the traditional MIPS address space, which, in order to run trap and emulate, we're basically confined to. You've got the user segment. All the user code runs within this low 2 gig of memory. The kernel sits in the unmapped cache segment here. And there's then an uncached version of that same mapping. So this is all fully mapped using the MMU. This and this segment, they direct map to the low 512 meg of physical memory. Then the top blue segments up there can be used by the kernel for its own mappings. That's used for things like vmalloc, which includes module code, which impacts us, as I'll show in a minute. So in order to run a guest, including the guest kernel, you can't run it in the kernel unmapped area because every single instruction will cause a trap. And obviously, you want to run the guest as fast as possible. So the solution to this was to basically allow KVM to emulate a different set of segments within the user area here. So we have a new guest kernel segment here, which KVM emulates. And so the guest kernel basically has to be relocated into that segment instead of its normal address in order to execute. You'll notice it's actually the same size as this. That's because we don't need the uncached segment. The uncached segment's usually used for memory mapped I/O. You usually want these to trap anyway, so you can actually get away with the guest kernel accessing them at the normal address in the red section, since you get a trap anyway. The guest user area is halved compared to normal. In practice, that doesn't actually affect any compatibility with any user mode programs because it's normally the kernel that sets up the mappings. when a program's loaded. For example, a stack would get set up growing downwards from there instead of from there. So obviously, if you're doing lots of trapping and emulative instructions, a lot of privileged instructions actually happen quite frequently, and that incurs a big overhead. So one of the techniques that was used to mitigate this is to actually replace instructions on the fly the first time they're emulated with instructions that don't trap. And one of the main instructions which does require trapping is the MFC and MTC 0 instructions. These basically move a value to or from a control register in the coprocessor 0 block. So they're used for basically reading and writing control registers, privileged sorts of registers. Many of these registers are actually, they're either read-only and don't change, or they're fully read-writable and don't have side effects. And so they sort of act like memory. And so we can actually get away with replacing them with loads and stores. But of course, in order to do a load or a store, you need an address in a register. And MIPS only has 16-bit offsets in its load and store instructions. But it does conveniently have a 0 register, which is hardwired to 0. And so what KVM Trap and Emulate does is it actually maps, it can map a page at address 0, or close to 0 potentially, while in guest kernel mode. And then it replaces these move to and move from coprocessor 0 instructions with straightforward reads and writes using 0 as the base register and a certain offset into that page in order to read and write the registers. And because that avoids traps the next time the instruction's executed, it can make things go a lot faster. It can basically half, for a kernel boot to a prompt, it can half that time using this and several other instructions replaced. So I'm going to move on to MIPS VZ now. This is basically an extension to the MIPS instructions set and architecture. It was introduced in release 5 of the MIPS 32 and MIPS 64 architectures. It basically gives you a partial guest coprocessor 0 state, which the guest kernel can access directly rather than through this trapping technique. And it adds a guest mode, which determines whether it's in the guest or not. This obviously allows far fewer traps into the hypervisor, ideally none, but there's always cases where you need them. It does also virtualize the guest physical memory. Obviously, you saw before with the segments that the kernel segments direct mapped to physical memory. So that's now all goes through the TLB as well. I'll get onto that as well. And this does allow you to run a completely unmodified MIPS kernel in VZ. There's actually VZ hardware in silicon already. MIPS Imagination have a few which haven't reached silicon yet. They've the P5600 core, which I've been working on, has it. KVM have their Octeon 3 cores, have MIPS VZ, their 64-bit cores. Similarly, Broadcom, their XLP9 cores, have VZ. Unfortunately, what this does mean is that there are 3 independent KVM ports for MIPS VZ. 2 of them have been posted to the list, one by Kemel Systems, again I mentioned them before, mainly aimed at MIPS 32 at the moment, and David Daney from KVM posted his as well, obviously aimed at the Octeon 3 64-bit processors. So there's a fair bit of work to do to unify these. So I'm going to talk a bit about TLB management. You may know that MIPS has a software-managed TLB. What this basically means, I mean, normally in a lot of processors, when you get a memory access happens and the CPU doesn't know about the mapping, it has hardware to go and walk the page tables in order to get a mapping to put into the TLB cache. Whereas with MIPS, instead of the hardware walking the page table, you'd normally get a TLB exception whose job it is to basically walk the page table and then write a value back into the TLB for it to use. This is normally like a bit of code which is generated at boot time, dynamically based on what core it's running on. So with Trap and Emulate, you've got exactly the same hardware because we want compatibility. So the bit on the left is the same, it's the same hardware. But the guest also wants to see the same interface. So it expects to write to the same sort of hardware. And so KVM in the middle has to basically do the munging itself. So when the guest does a memory access which isn't in the TLB, it will actually look through a completely software version of the guest's TLB in order to look for a mapping. It will literally linearly walk through them to find a mapping. If that fails, it will trigger a guest exception to allow the guests to fill into the guest TLB. And once that's done, that's still only a guest physical address that it gets from that. That's got to then be mapped to a real physical address, a host physical address, which it uses a guest PMAP table for that, which is currently linear. That's something else that needs improving. VZ moves a lot of this into the hardware. So you've still got the same TLB. However, it's now used just for the guest physical to host physical address. You've also got a guest TLB, which is like the rest of the coprocessor 0 state for the guest, is directly accessible while in guest mode without any traps to the hypervisor. So that now, when a guest does a memory access, which it doesn't know where it maps, it will trigger a guest TLB exception directly. The guest can then look in its page table, fill the entry back into the guest TLB. It will then trigger a root TLB exception, which can then do the rest of the mapping. It's worth noting that the TLB entries are shared between guests, and so there's an extra entry an extra field in the TLB entries called the guest ID, which differentiates the guests, and also between normal host mappings in here and the guest mappings as well. So I'm going to tell a bit of a war story. This was when we were bringing up MIPS VZ on the P5600 core. We'd had it fairly stable with a single core, a single guest, sorry, riddled out most of the hardware issues and software issues. But we still had problems when running multiple guests with CrashMe, which, in case you haven't heard of it, it generates random instructions and executes them, which can be quite a good method of soaking it. So when two guests were running, eventually, if you left it running for a few nights, one of them would lock up. And after a bit of debug, it turned out that the guest page size was getting switched to 4K. Basically, when Linux starts on Linux MIPS, it sets the page mask register. And that means that any TLB that gets written will have the right page size. But this register was getting set to 4K, which meant that all new mappings had 4K instead of 16K, which I was using at the time, which essentially, because the 4K wasn't covering the address that was missing in the TLB, it would infinitely try and fill a 4K page instead of a 16K page. So I was adding debug, so I added checks of the page mask register whenever the guest changed mode, and I ended up using CPU processor trace. PDTrace is the MIPS hardware trace in order to try and catch the control flow around this code when the page mask was changing. What was essentially happening, so this is the section of code just before the page mask was changed. A TLB mapping invalid. The TLB mapping is basically was invalid for the address that was being accessed from the guest, but a TLB entry still existed. This can happen because on MIPS, each TLB entry can map 2 consecutive pages. And so effectively, if this is the TLB, there's one page is mapped, but the other one's marked invalid. And so because the virtual address matches, you get a match, but it's invalid. So that causes a TLB invalid exception. The guest then started executing this. However, at this point, the guest was preempted, and another guest was allowed to run. The other guest eventually wrote a TLB entry, which happened to use the exact same TLB entry as the first guest. You'll notice the guest ID changed to 2, and any TLB entries that belong to another guest to the first guest will appear to be invalid. And so, when the first guest got to execute again a bit later, it still thinks that that TLB entry exists. It does a TLB probe, which this writes the index register with the index of the TLB that matches the address. But of course, none of them match now. So the high bit gets set, so it's invalid. But this particular code didn't actually check whether it was successful or not. So it later does a TLB read to read that index, which is invalid. And so all of the TLB entry registers got reset to their invalid state, including the page mask, back to 4K. So it turns out that actually this exception, it's a fairly reasonable thing to assume. It's always assumed it until now that the TLB entries aren't going to vanish while you're handling the TLB. So to fix this, basically you have to preserve certain TLB entries if you detect that this condition occurs. You don't really want to save them all, because certainly on modern cores, the new ones have an FTLB, which is much bigger. And so like the P5600 has 576 TLB entries. You really don't want to save them on every single context switch. And so you can detect this condition based on the exception level and the cause of the exception. And you know that the bad readdress register points to the address of the TLB causing the exception. And so you can look in the guest TLB whether there is a matching entry and save that and then restore it later. For trap and emulate, this problem doesn't affect it as much because the guest TLB isn't shared with any other guests. It's purely a software thing. It's not as volatile, basically. It still potentially could affect, say, VM, load VM, and migration, because when that happens, it doesn't save the full contents of the TLB. It would be a lot harder to hit, because obviously that happens far less than context switches, but it is a potential problem there. This could actually happen in several different cases. There's several exceptions, they're all fairly similar to the TLB invalid exception, basically where a mapping exists, but for whatever reason the exception still occurred. And potentially it's also a problem anywhere where the normal code does TLB management. This would normally happen with interrupts disabled, but if the index register points to a particular TLB entry, it can be assumed to exist. And so when you then do a TLB read, you've got the same problem. I was going to say something. So there's plenty more work to do. On the general front, we've got exposing various features to guests, such as floating point and MSA as the MIPS SIMD instruction set. That shouldn't be too much work, but it needs doing. Chappy and emulate, there's still low-hanging fruit for optimization, potentially, and a few fixes that need doing. For VZ, the big job really is to unify these different implementations and to get it upstream. There is efforts to do this. I've been meaning to do this, but have had my time diverted to other things recently, unfortunately. KVM have been doing a lot of work on their implementation recently, and it is apparently fairly stable. So that's probably going to be the one that it'll be based on, which will involve basically porting that to MIPS 32, making sure it works on MIPS 32 processors. After that, there is a MIPS IOMMU hardware, which, and the MIPS GIC, that's not the same as the ARM GIC, does have virtualization support, and VZ allows pass-through of interrupts straight to the guest. So it does allow device assignment in future. That's something else that we'll need looking at after this. So I'll put the links on the slides to the patch sets in case you're interested. But thank you for coming. And do you have any questions? Questions? Yes.
Just curious how the strap and emulate is implemented for your address space separation between kernel address space and user address space in the guest.
Yeah.
Is there something implemented? How did you do?
Okay, so the question was about how you implemented the protection within the guest segments, yeah? Yeah, so basically because the hypervisor always gets the TLB exceptions, it can choose to map them however it likes. And so it's literally, if it's within the guest kernel segment, it would, I'll go back to it, it would create a mapping directly to the low 512 meg of the guest RAM. And then if it's in this area here, it would then look into the guest TLB. Does that make sense? Does that answer your question? Yeah.
You play around with the TLB, and if I got you right, while you're emulating the instruction that is used for doing this as well, or something like that, right?
Yeah, I mean, in order to create the mapping, you write an entry into the TLB. So you just make sure that you only you'd write the entry that corresponds to that layout. So it's not arbitrary how this section is laid out. It's just designed to map roughly similar to the normal segment layout. So, okay, any other questions? Yeah.
I have seen that MIPS has cache coloring enabled for the 0 page. Did you have to do anything for KVM and cache coloring?
Do you mean with like cache aliasing?
I can explain that cache coloring thing. It's about a very old CPU, which actually checks a few more bits for a cache coherency conflict than it would actually have to. Those are the R4000 and 4400. So we're talking about 99 and 93 vintage processors. For everything else, before and after, this is not of interest.
Okay.
Yeah.
Yeah, so.
Yeah.
Doesn't matter.
And one of the interesting issues with that mapping at 0 obviously means that a kernel null pointer dereference doesn't cause a trap in the guest. That could potentially be fixed, I reckon, by just moving it up slightly because you've still got 16 bits of offset in the instruction. So you could map it at 12K from 0 and still have 0 unmapped. But yeah. Any other? Yes?
You have for MIPS VZ, you have performance data that kind of shows, I guess, how it compares to native, or curious what kind of performance you're seeing?
Not with me. No. No, sorry. Any other questions? Okay.
Considering that the number of KVM implementation is growing, in that case maybe with up to 3 implementations, have you thought about continuous integration testing? Like, are you tracking both KVM and QEMU trees and checking whether things are ready?
It's certainly something I want to set up. We do quite a lot of continuous integration of the kernel already, and we're wanting to do like boot testing and stuff. So that's the next step certainly. I want it to track QEMU and KVM and do that. Yeah. Currently, I've only got access to one of the VZ implementations. KVM have been doing a lot of work on it, so I'm still waiting to see their updates, which will allow me to then get working properly on the MIPS 32 side. So, yeah. Okay.
I assume that the T&E implementation would actually be testable using the emulation inside the QEMU?
Yes, so initially I was running it inside TCG QEMU. A guess within a guess within a guess. Yeah.
Actually look also into implementing the VZ stuff inside QEMU as well?
There is a QEMU team inside Imagination who have it on their radar. They've done the rest, various other bits for release 5, but they haven't started that yet. But it's certainly on the radar, yeah. Do you have a question? Oh. Okay, awesome. Okay, any other questions? Okay, thanks everyone for coming.